Okay, so in the last part of this lecture, having shown you some applications of expander graphs, explicit expander graphs, I'm going to start talking about actual constructions of explicit expander graphs. And there's actually several ways to make such constructions, and I'll survey them a little bit. Unfortunately, there won't be time to actually prove that any of these constructions work, but the proofs are not too bad, actually, and maybe we'll explore some on the homework. Okay, I must also confess that I got to do a bit of a bait and switch on you. So in the two applications we talked about, we used bipartite expander graphs, but I'm going to tell you about constructions of regular old non-bipartite graphs, which are expanders. And so let me just briefly tell you how you can take a regular graph with some expansion property and convert it into a bipartite graph with the kind of expansion properties that we use in applications. So I'll just sort of do this by some quick pictures. Let's say you have a regular old graph G. This will be a deregular, not necessarily bipartite graph. And it will always have n vertices. These will actually be two standing assumptions for all the graphs we talk about today. So let's say you have a graph like this and you've managed to show it has some good expansion properties. How can you get a bipartite graph out of it that hopefully has good expansion properties? There's actually two nice methods. So we're trying to get like a new bipartite graph over here. Oops, with some bipartite, with some expansion properties. One method is called taking the double cover of G. And what does that mean? It basically means you take your copy of G, and you take another copy of G, and each copy of G has some edges, and basically you make the edges go across instead of within G. Okay, and if G is deregular, then this double cover will also be deregular. And another way to explain it, an easy way to explain it, is if A is the adjacency matrix of G, then the adjacency matrix of the double cover, it has two n vertices, so it's twice as big, and it's bipartite, and it kind of looks like this. You put A here, and A transpose here, and zeros here. Okay, so if you think about it, that makes a bipartite graph, which is kind of like the one I just described. So that's one way to turn a regular, usual graph into a bipartite graph, and it often gives you the good expansion properties, or preserves the expansion properties. And another way is to make what's called the line graph. And this doesn't give you a balanced bipartite graph, but it gives you something pretty balanced if D is constant. For the line graph, you just make a bipartite graph where one set of vertices is associated with the original vertices V of G, and the other set of vertices is associated with, that's not a very good E, is associated with the original edges of G. And then you put an edge between a V vertex and an E vertex, if and only if that V vertex touches that E vertex back in the graph G. Okay, so each edge is, of course, connected to two vertices. So this graph will have regularity 2 on the right-hand side. And each vertex V is connected to D edges, so you'll have regularity D on the left-hand side. Okay, so let me just leave it at that. That's a couple of ways to get a bipartite graph, which hopefully is a good expander, out of a good expanding usual non-bipartite graph. The other aspect of the bait and switch was, in these bipartite graphs, we talked about vertex expansion, where, for every set of vertices here, let me switch colors briefly, every set of vertices here, if you look at its neighbors, if we call this S and this the neighborhood of S, then n of S had to have large cardinality whenever S was not too big. That's called vertex expansion. But now, when I go back to talking about usual non-bipartite graphs, you can talk about vertex expansion, but it's going to be easier, and it's a bit more common to talk about edge expansion. So let me just write these two things here, edge expansion. So from now on, I'm talking about not necessarily bipartite graphs versus vertex expansion. And so an edge expander is one that satisfies something like this for all sets of vertices S of cardinality at, let's say, most half the number of vertices n. The fraction of edges on the boundary of S is a good proportion of S itself. Or to put it in this probabilistic way, if you choose a random edge UV, the probability that U is in S, given that, well, let me just say, sorry, that V is in S, given that, sorry, V is not in S, given that U is in S, is at least epsilon. Okay, it took me a couple tries there, but what I want to say is that another way to put it is if you pick a random vertex in the set S, uniformly at random, and take one step in the random walk, the probability of you escaping S is big. It's at least epsilon. Okay, that's edge expansion. And vertex expansion is a condition that looks like this for all sets S, again, maybe of size at most n over 2, or some constant fraction of n. The cardinality of the vertex neighborhood of S is at least some epsilon times, the maximum it could be epsilon times d, times the cardinality of S. Okay, and as it turns out, in the study of expander graphs, it's more convenient to study edge expansion. It's a little bit easier, but they're not unrelated. Now, in fact, I have to pull one more switch on you, which is that finally in the study of expander graphs, it's even more usual not to study this edge expansion parameter epsilon, but rather to study the second smallest eigenvalue of the graph's Laplacian. Okay, so let me repeat that. It's even more typical to study what you might call lambda 1. This is the second smallest eigenvalue of G's Laplacian, your graph's Laplacian, which, let me just remind you, L, it's normalized Laplacian, it's the identity matrix minus the normalized adjacency matrix. Okay, so we're in the setting of regular graphs now here. So A is the adjacency matrix of the graph, 1 over D is the normalized adjacency matrix, and the Laplacian is the identity minus that. And as we saw in the spectral graph theory lectures, this matrix always has an eigenvalue of 0. That's equivalent to saying that A always has an eigenvalue of D. And what controls the expansion is the second smallest eigenvalue, which we call lambda 1. Okay, and what we saw in previous lectures was this thing Cheeger's inequality, which relates this lambda 1 to the best epsilon you can put here. This is really, I mean, the best epsilon you can put here again is this minimum conductance of the graph G. And we know that these two things are related up to a square or up to a square root, depending on how you put it. So in particular, let's say relates this lambda 1 and epsilon. So in particular, actually, it's even harder in some sense to construct a graph whose lambda 1 is big than it is to construct a graph whose edge expansion parameter epsilon is big. This is the easy direction of Cheeger's inequality. If you construct a graph which has a lambda 1 that's large, then, well, in fact, just lambda 1 is at least epsilon. Sorry, wait a minute. Wrong way around. Lambda 1 is at most epsilon. Maybe there's a factor of 2 or a half, or sorry if I'm getting this slightly wrong. But what it means is if you manage to construct a graph whose lambda 1 is large, then automatically its edge expansion is large. And that's the easy direction of Cheeger's inequality. Let me just put a little squiggle here to denote up to a constant factor. The hard direction of Cheeger's inequality is that also if lambda 1 is large, then epsilon, the edge expansion parameter, is also kind of large up to a square. Okay, so this two-sided inequality says that if you're interested in edge expansion, then and you're being a bit qualitative about things, then it suffices to study this eigenvalue. And that's what we'll do, because in some sense, the second smallest eigenvalue has a polynomial time algorithm for computing it, so it's somehow easy to understand mathematically, it's characterizable. Whereas as we saw, this minimum edge expansion parameter, this minimum conductance, is NP hard to compute, so it's hard to get your finger on it mathematically. And so what we're eventually going to talk about constructing, and what everybody or most people when they're constructing expander graphs strive to do is they strive to get what's called an n, d, epsilon spectral expander. And what does this mean? This means a d-regular n-vertex graph G with second smallest eigenvalue of the Laplacian, lambda 1, at least epsilon. So sorry I'm using same parameter epsilon here. Let me call this epsilon 0 and this epsilon 0. Okay, and if you have such a spectral expander, then by the easy side of Cheeger's inequality, it's even a good edge expander. You can also show, this is not too hard, that if you have a good spectral expander, it implies you have pretty decent, let me just put that in quotes, vertex expansion as well. This was originally proved by Alone and Millman, and it's a consequence of the tight form of the expander mixing lemma, which we'll mention shortly. But all of which is just to say that I want to convince you that if you can construct these spectral expanders, then they give you, good edge expanders, and therefore, and also good vertex expanders, and also you can get good bipartite expanders, and so forth and so on. So this will be our task for talking about this will be our task for the remainder of the lecture. And let me just mention here that it can also be good to think about the eigenvalues of A, or this matrix K. So this is, let me erase this up here. This was I minus K, where K is the transition matrix for the graph, 1 over D times A. And this K had eigenvalues that we called, let's see, what do we call them? Kappa, I think we called them kappa 0 through kappa n minus 1 as well. And they satisfied, well, they're just 1 minus the lambdas. So they satisfied that 1 is equal to kappa 0, greater than or equal to kappa 1, greater than or equal to dot dot dot, greater than or equal to kappa n minus 1. Okay, and so just as L had a trivial eigenvalue of 0, K has this trivial eigenvalue of 1. And so the key parameter is kappa 1. In particular, the key interest is like how far away from 1 it is. So we're interested, we call it, an expander, a spectral expander, when kappa 1 is less than or equal to 1 minus epsilon 0. That's equivalent to this condition on lambda 1 being at least epsilon 0. Okay, that was a little bit messy, but let me now say we're just focused on constructing explicit n-vertex graphs that are n d epsilon 0 or epsilon spectral expanders. And as I mentioned before, what we really want to do is fix some d, like a really fixed constant like, I don't know, 3 or 4 or 8 or 50. And then get some epsilon 0, which is strictly positive constant, 0.001 is kind of okay for us. And then what we want is n, d, epsilon spectral expanding graphs for arbitrarily large n. Okay, we don't have to get them for every n, but like maybe every n that's a power of 2 or every n that's a square or something would be fine for us. But we want, like a large infinite family of these graphs. And what we really want is for them to be deterministically constructible in poly n time. And what we really, really want is for them to be fully explicit, which kind of means that you could even get like a 2 to the n vertex such graph with its adjacency matrix or adjacency list computable in poly n time. Okay, so on with the show. Let me tell you about 3 constructions. And the first construction, it's really great because it's like unbelievably explicit. It's like so explicit. You just write it down, and the proof that it's a spectral expander is not so bad. So this construction basically originally due to Margulis from 1973. Actually, the day I'm recording this, Margulis won the Abel Prize. So congratulations, Grigory, and thanks for the expander graphs. He's actually going to show up in construction 2 as well. But there's a subsequent paper by Gabber and Galil from 81, which kind of tidied things up a bit. And so, we don't need to give Margulis too much credit. So these are often referred to as the Gabber-Galil expanders. And the nicest analysis of them was done in a subsequent paper by Jimbo and Maruoka. Okay, so without further ado, what is this graph? Family of graphs. So you pick a parameter m, and then the vertex set for your graph, v, will be the integers mod m squared. Okay, so you think of it as like a grid. Here's a m equals 4 example. And, you know, these vertices are indexed by pairs, x, y, where x and y are integers mod m. Okay, that's the vertex set. And what's the edge set? Well, you connect a given vertex xy to the following 8 vertices. I have to copy them off my screen here. X plus, yikes, x plus, oops, plus y, comma y. That's the first neighbor of xy. X minus y, comma y. That's the second neighbor. And you also do x plus or minus y plus 1, comma y. That's the third and fourth neighbors. And then you do a symmetric thing. So you connect it to x, comma y plus or minus x. That's the fifth and sixth neighbors. And x, comma y plus or minus x plus 1. And that's it. So D equals 8. And this is a wonderful expander, family of expander graphs, one for each m. So you have an expander graph for every n, which is a square, for several reasons. First of all, well, let me just state the theorem. The theorem is that this is an m squared, comma 8, comma, epsilon 0 spectral expander for some strictly positive constant epsilon 0, which, you have to kind of squint into the Gabber-Galil proof or whatever, but I think maybe like epsilon 0, like 0.1 or something. Okay, so the actual expansion parameter is not like amazing. It's 0.1, that's okay. But it's got so many other great properties. First of all, it's, as I mentioned, strongly explicit or fully explicit. I mean, it's as great as you can get. What that means is, there's absolutely no trouble in, like, for a poly n time algorithm imagining one of these graphs and working with one of these graphs on 2 to the n vertices. Because these, names of vertices are just pairs of, numbers, mod m. So if you can imagine if like m is, let's say, 2 to the n, so these vertices are just named by pairs of n-bit strings. And, if I give you a particular pair of n-bit strings, it's super easy to compute the 8 neighbors of these strings. You can do that in linear time, order n time. It's just some addition. So these are brilliant, strongly explicit graphs. The degree is 8. That's very nice. It means if you want to take a random walk in this, even this exponentially sized graph, then every time you take a step, you use 3 random bits to pick a random neighbor out of the 8 possibilities. So that's great. And that's all I'll say about it. I mean, the analysis of it is kind of a drag, but it's like 2 pages of elementary linear algebra that you can look up online. James Lee and Luca Trevisan have good expositions of it, for example. Okay, so that's the first expander I want to tell you about. The second family of expanders I want to tell you about are actually the so-called Ramanujan graphs, and let me warm up to them. So, as I mentioned before, a random deregular graph is an excellent expander. It's got great edge expansion. The only trouble with it is it's not explicit. But it's way better even than these kind of expanders we've been talking about. So like here, epsilon 0 is 0.1, but for a random graph, the second smallest of the eigenvalue of the Laplacian is super close to 1. Like, it's amazingly large. Perhaps a better way to look at it in the context of a random deregular graph, let's say you have a random, okay, let's say we have a random deregular graph. A good way to get such a graph, by the way, when n is even, is to pick d random matchings on the n vertices. It's very clear how to pick a random matching and then just superimpose them. This is a good way to get a random deregular graph. In a random deregular graph, let k, which is, okay, let's call it G. Let k be 1 over d times the adjacency matrix A, as usual. So this, as I mentioned before, has eigenvalues 1. That's the trivial eigenvalue. Kappa 0. And then the next eigenvalue is kappa 1. The next one is kappa 2, down to kappa n minus 1. And to be a good expander, we want this kappa 1 to be far from 1, bounded away from 1. And it turns out, from this point of view, in a random deregular graph, not only is it kappa 1 bounded away from 1, it's super close to 0. And in fact, all the eigenvalues other than kappa 0 are super close to 0. And this is a theorem, a very famous and difficult theorem due to Friedman from 2000 maybe? It's famously like a 100-page paper, although it's been recently simplified to, I don't know, 20 or 30 pages. But the theorem is that in a random deregular graph, all of these eigenvalues, kappa 1 through kappa n minus 1 in magnitude, are at most basically 2 times root d minus 1 over d. Okay, plus little o of 1. That says n goes to infinity. Yeah. Oh, sorry, with high probability. With probability, also 1 minus little o of 1. Okay, so Friedman's theorem says with high probability, you pick a random deregular graph G, and you look at this eigenvalues of its transition matrix. You're hoping that they're all, other than the trivial one, they're all bounded away from 1. And in fact, they're all super close to 0. So this is the exact magic number, but you know, in your head, you can just think of this as asymptotic to 2 over root d. Okay, so if you make d like a big number, this is really close to 0, a big constant. Okay, and that's kind of awesome. And what we'd like to do is get explicit graphs that are close to this. And in fact, for some values of d, you can get this bang on. And this is called Ramanujan graphs. Okay, so what is a Ramanujan graph? It was fancifully named by Lubotzky, Phillips, and Sarnak in '88 when they constructed these graphs that are explicit expanders. Basically, they're explicit deregular expanders that have exactly this eigenvalue property. And they're actually constructed independently at the same time by Margulis, also in '88. And it's said that they're also implicitly constructed in the late 60s by Ihara. And as I said, what are they? They're deregular graphs G, and they have all of these kappa i's, at most, this exact magic number, 2 root d minus 1 over d, literally exactly, with no plus little o of 1. So these are actually kind of amazing because they're, in some sense, like better than random graphs. Okay, by a little o of 1, but that's nice. But here's a little bit of a catch. The construction of these requires very heavy-duty number theory, like super hard, super deep. Well, the construction itself is actually not very complicated, okay? You know, the vertex set is like all the 2x2 matrices with ones in the diagonal and the other 0 down here and some number mod p in the other entry. And the edges are not hard to say what they are, but the analysis that proves that they're expander graphs and that they have this expansion property is like super, super duper hard. It uses some deep number theoretic results of Pedersen, which are generalizations of some results by Ramanujan. So that's why they were called Ramanujan graphs. And there's another number theory catch, which is that they only showed them when you need that d minus 1 is a prime, which is congruent to 1 mod 4. Okay, so you don't get them for every value of d. Well, you get them for like a bunch of values of d, whenever d minus 1 is a prime. And actually, this was subsequently improved by Morgenstern in like 94 or something, to the case where any case when there's a finite field of size d minus 1. So d minus 1 being a prime power. So that's great. And these are also, they're definitely explicit. I think they're strongly explicit too, or maybe there's like some tiny caveat, but let me just say basically they're also strongly explicit. And that's great too. So these are wonderful graphs. Again, they're, let's say strongly explicit, basically explicit. For any d minus 1 that's a prime power, you just write them down, and writing down the graph is not hard. The proof that they're great expanders, spectral expanders, is super hard, but they're actually like optimal spectral expanders. It's actually known that you cannot get anything better than this magic number, 2 root d minus 1 over d, basically 2 over root d. And that's, you know, it's really close to 0. So it's like, the epsilon 0 in the definition of spectral expander is really close to 1. It's like 1 minus 2 over root d. Yeah, so these are great as well. Another thing that is nice about them, there's a corollary of their number theoretic construction. Well, this corollary also takes work, but I like to mention it because it's like a super cute explicit construction of an expander graph that results after you work through all the number theory in their paper. It's this. Consider the graph where you let v be the integers mod p, where p is a prime. And now, what are the edges? Well, you connect a vertex or number a to a plus 1 and a minus 1. And one other thing, but so far a plus 1 and a minus 1 like makes just a ring, a cycle. And the last thing you connect a to is 1 over a, mod p. Okay, and the pedants will ask, what about if a is 0? Well, you treat 1 over 0 as 0. So you can just like put a self loop on 0. Okay, and so this gives you like chords. You know, 1 over a is, if you do it twice, you get back to a. So this makes an undirected graph, and it gives you some chords. And they're pretty pseudo-random, as it turns out. And indeed, this is enough to give you a 3 regular explicit expander. Okay, so the theorem is that this is like a n comma 3, well, I suppose I should say p comma 3 comma epsilon 0 spectral expander. And the epsilon 0 is really not great. I think it's, I don't know, like 1 over 100 or something. But hey, it's a positive constant. Okay, remember that means that all the eigenvalues, the second smallest eigenvalue of the Laplacian of this graph is at least 1 over 100, or the second largest eigenvalue of k equals 1/3 a is at most 99 over 100. Okay, so that's all I wanted to say about Ramanujan type expanders. And the last family of expanders I want to talk about is what might be called Zig-Zag esque expander graphs. Okay, so these kinds of expander graphs were developed by Reingold, Vadhan, and Wigderson a little while ago. And what's cool about them is they're like an explicit iterative construction of larger and larger expander graphs, which is nice. And the analysis is pretty combinatorial, so you don't need any of the crazy hard number theory of the Ramanujan graphs, and you don't need the somewhat long and painful, well, it's not so bad, but kind of long and mysterious linear algebra-based proof of the Gabber-Galil expander graphs. And one more key aspect of this zigzag style expander graphs is actually these are the only known way to get those like really good bipartite expander graphs that we use in the applications. Well, we only really needed it for the coding application. If you remember way back when we talked about these bipartite expanders, we used the fact that the expansion from the left side to the right side was at least 0.8 times the maximum possible thing. Like every set S here expanded to a set of vertices of size at least 0.8 times D times cardinality of S. And getting that 0.8 is pretty hard. And this zigzag-based method is the only current known way to achieve it. So that's another good thing about the zigzag-based method. Now, I'm not going to tell you exactly what is this like zigzag method for constructing expander graphs, because subsequently to its appearing, people realized there's like slightly less complicated ways you could get similar iterative construction of expander graphs. Maybe again, not with these ability to construct these great bipartite expanders, but like sort of easier to analyze. And one method uses what's called the replacement product for graphs. And another method, which was recently developed by Dan Spielman in his course lecture notes, uses some kind of like a line graph product method. And probably one of these will be on the homework. I won't have time to prove everything. But these are sort of like slightly simpler than the zigzag product-based method of constructing expander graphs. So let me briefly sketch for you the idea behind the replacement product construction. And this replacement product of graphs is a way to take two graphs and put them together to make a bigger graph. And it originally was analyzed in a paper prior to the zigzag stuff by Jeremson, Tetely, and Vigoda. And, well, let me just quickly say, here's the idea, which perhaps will be explored on homework. Let G be a, well, an n, comma, capital D, comma, epsilon sub G spectral expander. And let H be capital D, little d, epsilon sub H spectral expander. Okay, and the funny thing here is the number of vertices of H is equal to the degree of G. So think of G as like a big graph, and think of H as like a little graph. And they have this compatibility condition that the number of vertices of H is equal to the degree of G. And there's this thing called replacement product. So it's like R in a circle that takes G and H and makes like a new, even bigger graph. This is a G replacement product H. And it's going to have some nice properties. So I can even tell you how this replacement product graph works. Even though I said G was a big graph, let's try this graph for G. This is an example here. Okay, this is not even a regular graph, but okay, don't worry about it so much. So this is a 3 regular graph. So you would need to, that's capital D equals 3. So to replacement product it with H, you would need a little 3 regular graph, maybe a triangle. That's H. And how does the replacement product work? Basically, you put a copy of H at every vertex of G. So let's do that. And then you put edges between these copies in the way that G had edges. So we need some like edges here, and some edges here, and some edges here, and here, and here, and maybe also some self loops. And every vertex of G has degree 3, and now the associated kind of cloud of vertices has 3 vertices. So you can actually associate each vertex here with one of the outgoing edges. And so like every vertex in one of these clouds has like one outgoing edge. Okay, and so every vertex gets like one outgoing edge. Okay, hopefully that was kind of clear. And in fact, to make it simple, I lied. It has one outgoing edge. Each of these, in H, the degree is little d. So in each one of these copies of H, every vertex has d sort of internal edge, internal neighbors. And instead of having each vertex have one external neighbor, you make it have d parallel external neighbors. D parallel edges as its external neighbors. So you actually just like make 3 copies of each of these edges. And the reason to do that is so that when you take now finally a random walk in this big graph, every vertex has like little d internal edges and little d like external crossing edges. Okay, and so that's set up so that when you take a random walk, at every step you have a half chance of doing an internal step and a half chance of doing an external step. Okay, and okay, when you do this construction, what are the properties of the new graph G replacement product H? Well, it has d times n vertices, because, well, we have G had n vertices and H had capital D vertices, and its new degree is 2 times little d. That's because I said, remember, little h has d is little d regular, but we also, for each vertex in it, have d like external edges. So every vertex has d plus d edges that it touches. And the theorem, that's basically in this Jaramson, Tedley, Vigoda paper, is that it also has pretty good spectral expansion. Its spectral expansion is epsilon h times epsilon g over 16. Okay, so if epsilon h and epsilon g are both like, constants, you multiply them together, you still get like a positive constant over 16. And, the idea is that, G is expander, so it's kind of like well-connected, and H is also an expander, so it's kind of well-connected, and you put them together in this way, and, it should also be pretty well connected. So this is a way of taking 2 smaller graphs. You think of G as like pretty big, H is like a constant size, and making like, a constantly bigger graph. So what happened here? The number of vertices went up. The idea is we're going to start, with some expander G, and we'll do this replacement product with H and try to get a bigger expander. So the number of vertices went up. That's good. It allows us to make bigger graphs. And the degree actually went down. If you think about G's degree was D, and now it went down to 2 times little d. So that's good. We kept the degree nice and small. The only trouble is that the this eigenvalue went down. I mean, let's say if you think of your big graph G as the main graph, it used to be epsilon G, and now you multiplied it by epsilon H over 16. So you kind of shrunk it. And that's bad. But it's not so bad. Okay, we kept the degree small. We made a bigger graph. Okay, the spectrum went down. Let's do a different move to make the this eigenvalue bound go back up. And one thing you can do is, if you have a graph G, another move you can do is square it. So the squaring of a graph has the same vertex set. And you put an edge between U and V if there's a length 2 path from U to V in G. Actually, this is not totally accurate. What you should do is put, if there are L different length 2 paths from U to V, then you should put L parallel edges from U to V. Another way to put it is simply that the adjacency matrix gets squared. That's exactly what's going on here. And what happens when you do this? Well, the number of vertices stays the same. The degree goes from d to d squared, because that's how many length 2 paths you have. And, well, it's not hard to show that the eigenvalues of a squared are the squares of the eigenvalues of a. And that's also true for the transition matrix K. The eigenvalues of K squared are the squares of the eigenvalues of K. So every, like, kappa I just goes to kappa I squared. Okay, so if these kappa i's were all at most 1 minus epsilon in absolute value, then now they're all at most 1 minus epsilon squared in absolute value. So the gap went from, the so-called gap from 1 went from epsilon to, well, around 2 epsilon. Okay, maybe 2 epsilon minus epsilon squared, but never mind about that. Basically 2 epsilon. So the point is this made the eigenvalue parameter, this eigenvalue gap, go up. Okay, so this gap went up by a factor of 2. That's great. The number of vertices stayed the same. That's fine. And the degree went up. And that's kind of bad. But we can now put these two moves together, right? Because the replacement product makes the number of vertices get bigger. That's good. And it brings degrees down. So if you make degrees go up, then you can bring them back down with the replacement product. And the replacement product makes the eigenvalue bound go down, but squaring makes it go back up. So that's good, and you can kind of iteratively interleave these and get good results. Actually, more generally, what you can do is look at the teeth power of G, where t is an integer parameter. This is the graph whose adjacency matrix is a to the power of t, or you put L edges between u and v if there are L paths of length t from u to v. And in general, this has n vertices if the previous one had n vertices, and the degree goes from d to d to the power of t, and the eigenvalue gap epsilon basically goes up to around t times epsilon. Okay, that's ignoring these like lower order terms. Okay, so, right, so you can now iterate this, as I said. So how does this iteration work? I'm just sketching things here, but perhaps the full details will be on the homework. Let's say if H, so H is this like small expander graph that you're gonna start with at the beginning and keep using over and over again as your replacement product friend, and G is like a graph that's getting bigger and bigger and bigger. So let's say H is a graph that has little d equals 4. Okay, 4 regular graph. And let's say its number of vertices is 8 to the power of t, and its second smallest eigenvalue of its Laplacian, lambda 1, is at least, I don't know, like 16 over t or something. Okay, what I claim is that such a graph H exists. So just buy that claim for now. So what happens? So now if we interleave, we start with a graph, well, we can start with a graph G, and now we interleave the replacement product and this power of t operation. And what happens? So we replacement product, and the degree becomes 2 times little d, which is 8. And let's see. Right, let's work this out. Okay, let's go back to our replacement product here. Good. So this capital D, which is the number of vertices of H, was like 8 to the power of t. So when we do this replacement product, the number of vertices goes up by this constant factor 8 to the t, and the degree is 2d, and the eigenvalue bound goes down by epsilon h over 18, and this is like the epsilon h over, what did I say? 16. This is epsilon h. So this goes up by, it goes down by this over 16, which is about, the eigenvalue gap goes down by around 1 over t. Okay, but then when we power of t, the eigenvalue, power of t, the eigenvalue gap, basically goes back up by t. So basically the eigenvalue gap stays constant when you do these two operations. And the number of vertices is getting larger and larger by a factor of 8 to the t at each step. Okay, and the point is that, right, since the degree of the graph at each step is 8, when you raise it to the power of t in this step, the degree goes to 8 to the t, which is the number of vertices in H. Okay, so I got a little bit muddled there, but I think it all matches up. And then when you, replacement product, this goes back down to 2 times little d, which is 8. Okay, so the degree goes from 8 to the t, back down to 8, and so forth. And the eigenvalue gap goes up by a factor of, goes down by a factor of 1 over t, but it goes back up by a factor of t, and so forth and so on. Okay, and this is great. It makes bigger and bigger graphs, constant degree 8. Eigenvalue is like some absolute constant. And actually, really all you need to make this work is like a starting graph h. So you just need like a starting graph h, which has these properties for some t, with these properties for some t, the required properties for some t, and you just have to argue that that graph exists, because then, an algorithm can find it in constant time, and indeed such a graph exists, an h exists. It can be shown with t being, I don't know, like 30 or something. I somehow convinced myself of that, like a random graph will have these properties. Okay, so actually this last step is makes it not so practical that you have to like brute force search for this, but actually there are other ways you can take like a little mini expander using one of the other constructions, like a Ramanujan graph or something, just to assure yourself that this finite graph exists, and then you can use it in this iterative process to make bigger and bigger expander graphs. Okay, so this is basically the idea of the zigzag product. This is the replacement graph version. And as I mentioned, one great utility of this is it's the only known way to make some of these most sophisticated bipartite expanders with really great expansion. So those are 3-ish different ways you can get explicit expander graphs for your many applications, coding theory, de-randomization, and whatnot.